Hi, my name is Balaji Balakrishna. I'm doing a product management course in Coursera with Duke University. As part of this course, I have a project to demonstrate and build a model to predict the electrical energy output of a combined cycle power plant. So the data set has given with 9,568 hourly average ambient environmental readings from the sensors at the power plant, which I'm going to use the model. So that consists of variables such as like temperature, ambient pressure, relative humidity, exhaust vacuum, the final one, electrical energy output. So here is a data set that I have extracted that has total 9,568 records. So by looking at the data, this problem is like a supervised regression task since we are predicting a continuous numerical value, which is the power output in megavolts. So I distinguish this data based on the train versus test data. So the train data is going to be like 80% of the data, which is like 7605 records, and the test data is 20%, which is going to be like 1963 records, right? So then I have extracted all the train data into like a different tab to calculate the linear regression model. So here is the regression output that I performed based on the train data. Here I can see the coefficients and the standard error for this, which is like 4.55, okay, and the total observed records was 7605, right? So let me walk through how I was able to build this model and how RMSE was calculated, right? So then I can show you the final output. So the first thing what I did was by looking at the data itself, I figured out this is like a supervised regression problem. So I have to evaluate the performance of the model. I used root mean squared error because it provides a measure of how far the predictions are from the actual values and penalizes larger errors more heavily. Okay. So next one, the features and the models, right? So the features that I have used in this model is the temperature, exhaust vacuum, ambient pressure, relative humidity. So I selected all variable environment variables as features since they influence power generation. And algorithms that I considered what I built two compared two models. The first one was the model one, which is the like a baseline, the linear regression with a single feature that is based on the temperature. And the model two is the final model, a linear regression with all the features, AT, V, AP, RH. So I compared a single model with one variable to a more complete model with all the features, right? So the goal was to determine whether adding more variables improves the model's predictive performance. Then data splitting. So as I said, I split the data set into 80% training data and 20% test data. The model was trained exclusively on the training data set to avoid the data leakage. So using Excel's regression tool, I trained a multiple linear regression model on the training data and obtained the coefficients for each feature, which you can see here. I then used these coefficients to build the prediction equation and applied it to the test data set to generate prediction power output values. So you can see here on the final output how I was able to get this 4.61. So here is the actual P and here is the predicted P, and the difference of these two is 0.91. Then is a square of this squared error is 0.83. So RMSE was calculated by using this all the train regression output, the coefficients, and the variables 1, 2, 3, 4. Okay. So then going back to um, a model evaluation, right? To evaluate the model, which I said I compared the data between the model 1 and model 2. The finally I can see that model 2 has a better accuracy because we are taking all the variables on this one, right? So overall, to evaluate the model, I calculated the prediction error for each row in the test data set and then computed the squared errors, which I explained here, right? So the overall I got RMSE was 4.61. This means that on average, the model's predictions are within about 4 to 5 megavolts, and the actual power output, which is relatively small error given the total range of output is between 420 and 495 megawatts. So this is the final the model equation that I applied to get the RMSE 4.61, right? So the model interpretation here. In terms of interpretation, the temperature had the strongest negative impact on power output, meaning that higher temperature reduces the efficiency of the power plant. So the exact vacuum also had a negative effect, while ambient pressure showed a small positive relationship with power output, and relative humidity had a minor negative impact. So the overall the results are consistent with real world expectations for power plant performance. So the conclusion here I can see in my Excel model, including the regression output, predicted values and RMSE calculation. Overall, the model performs well and demonstrates strong predicted capability using simple linear regression and environment data. With that, I'm going to show the final output here. This is how I calculated RMSE. Hope that clarified everything how I predicted the model. Thank you very much.